the idea is that I would like to share a project that I started past summer, working with an excellent group of scientists at the Arecibo Observatory. And this project is an application of statistics, in particular a method that is called Spectral Kurtosis estimator. And the idea is that these methods allow us to identify what is known as radio frequency interference in radio astronomical data, and not only allow us to detect, but also to perform what is called an incision. Okay. In particular, the main instrument that we use in this work is the 12-meter of Arecibo telescope, which was recently operated, and I'm going to talk about that soon. So this is a project in collaboration with Dr. Alison Smith from UPR Mayagüez, and also Dr. Anish Roshi and one of undergrad students, Alexander C. And that are from University in Central Florida. Okay. So let's see if we can. Okay, perfect. So let's go for the introduction. The objective of this project is to detect and perform an excision of radio frequency interference in radio astronomy data from a pilot survey of a molecule that is called metadaline. And this molecule, the emission transmission is observed, at least the main transition, at the 3.3 gigahertz frequency. And our focus is on the galactic plane, okay? And how we're gonna detect and perform the incision of the interference in our data is by a statistical method that is called general kurtosis estimator, and that's the idea. So first, what I need to define is what is radio frequency interference, right? So when we have an antenna, a dish, or a radio telescope, right? So, for example, like the 12-meter in Arecibo Observatory, what we are doing is just detecting, receiving radio wave signals. And the idea is that that is, for example, from the natural emission of the molecules, right? But also we, for example, create man-made transmitters. And those transmitters also interfere with the signal that the telescope is receiving. Saludos, estudiantes, bienvenidos. Sí. So that's the main idea. And then my first question to you all, students that are in the Zoom and also here in the room. What do you can you mention any man-made transmission a transistor that typically we can have? So we almost carry one with ourselves, and it's our cell phones, right? So cell phones are a high source of radio interference, right? So that's why whenever you get to a radio observatory, the first thing that you see, the big sign is what either put your cell phone in airplane mode or turn it off, even better, right? So that's just one of the many examples. We can have also security cameras, Wi-Fi routers, and many other devices. And the idea is that as innovation and technologies progresses, so these mechanisms of man-made transistors are more complex, right? So sí, excelente. An excellent one is the microwave that we use in our homes. Absolutely, even cars as well, right? So all that. So RFI in radio astronomy is something that we have to learn how to deal with it and study deeply, characterize it, And so that's one of my main objectives, is just to learn a statistical method so that we can, for example, have routines that systematically or automated clean the data. Let's just put it in those terms. Okay, so that's the idea. The importance also of performing this type of statistical methods is that we can salvage a lot of astronomical data. Right? When we do observations, we collect data, and that data is what is called RFI affected. So then, and if those RFI, that RFI, that interference is located very close to the main frequency line emission that we have, so we cannot use that data. That's the idea. Okay. So the idea is like we have the data and we want to clean it because we want to save the data. And the more data that we can save, the more data that we can have to process. And the idea is that we can then improve, very important in radio astronomy, especially in spectral line, right, is to improve the signal-to-noise ratio of a detection of a molecule. Okay, so in simple terms, that's what we have. So the idea is to improve the efficiency of observations, as I mentioned before, on, for example, right now for our project, we work in what is called S-band. There are many other bands, but S-band particularly is known for being RFI polluted. So this is an important method that will help us to improve the efficiency of our observations, right? And in that way, we would like to maximize the potential of what? Of the devices that we use, the instrumentation. In this case, the main instrument was the 12-meter in Arecibo telescope, Arecibo Observatory. If you have any questions, feel free to share your comments. Okay, please. I would like to do it like that. So what I'm doing right now in this particular research project, right, is just a step on a more ample and more, let's say, ambitious research research goal that we have. And the idea is that we would love to be able to again use the 12-meter in Arecibo Observatory. And the idea is to produce a large-scale molecular survey of this molecule in particular, or CH, at this frequency, and on the galactic plane. And that's have a lot of benefits, in terms of the usage that the scientific community can give to this survey map. Okay, that's the idea. So one of the these, for example, we represent if we're this will, for example, we represent the first high sensitive map in the galactic plane, and this will help us to determine the abundance or the distribution of CH with respect to other molecules, for example, like CO and OH. Okay, and as well as neutral hydrogen. And the idea is that this is beneficial to the community in general if we accomplish to do this, because then we can apply to test astrochemical models. And not only that, but also knowing information about the distribution of CH in these molecular clouds help us to, for example, delineate various stages on the evolution of on our understanding of evolution of the early stars. Okay, the development of the early stars. So that's the main goal in big as a broad goal, right? So what we did in particular this summer was a pilot survey. We were able to have enough time of observation to produce a 3 degree by 1 degree map on the galactic center for CH. And right now we are working on the much reduced data, just on the 1 by 1 degree on the galactic center. And the idea is that on all observations that we did perform, we have evidence or that suggests a detection of CH in all of this. So we are very excited. But first, we need to pass through this first step of the pipeline, the reduction data pipeline, which is cleaning the data from RFI. Okay, so that's the main idea. So that you guys can have a clear idea of how these maps may look. This is a map of the neutral hydrogen, right? And what we can see, this is all the galactic plane. Here we have, for example, the galactic center. And this is just, my purpose with this is just to show that hydrogen is like everywhere. In particular, right, it's very focused on, very concentrated in the galactic plane, okay? So this is another one, another map. In this one in particular is CO. The galactic center is shifted towards this part, okay? That's why we have like this more intense color, etc. And this is a map for CO. And the idea is that this map, for example, was done with a telescope of 1.2 meter. And it took of about 10 years to accomplish the full map. And this was from the telescope was located, I believe, that in Harvard University. Okay, so what we want to do in our case is just to do a similar map, but for CH. That's the idea. And right now, what we have is just a 3 by 1 degree. So we would like to span the whole galactic plane if possible, right? That's our goal. So, for example, this is the main instrument. It's called 12 meter because the dish, the diameter of the dish is has like 12 meters. And recently was operated. This happens last June. And immediately after the upgrade, we were commissioning the observations. And the idea is that before the receiver of the telescope used to have a room temperature or warm receiver. But now with this technology, the cryogenic receiver, so what we can have is just a cooling system. And the idea is that improves our sensitivity for the detection of emissions. Because the whole system, right, if it's like cools down, so it's able to detect more. So that's one way of increasing the sensitivity of a device, right? It's one variable is just the surface area of the antenna, and the other variable is also the temperature of the whole electronic equipment, right? So here we have like Felix Hernandez. He was one of the many engineers that worked very diligent to install the receiver. Okay, so that was the idea. This I include here a couple, for example, of numbers important to the telescope. For example, we have the surface RMS. This number is an indication of how good, of the design, of the form, of how close is the dish from a paraboloid. Okay, and that's super crucial, right, for the performance of the equipment. You guys know that. And here, for example, is a picture of the fifth horn that was the fifth horn that was installed in the receiver here in this part, right? Let me see. And this is Dr. Anish Roshi explaining to Dr. Mayla Lebron and me all the features of this fed horn. Okay, so that was very exciting. So right now, all this that you have here, you know, is located here, for example.
The surface of that, it looks really rusted. That's not such a long time, but they have to do something for these types of issues.
Yeah, okay. Perfect. So something that I would like to point out is that the beamwidth, for example, right, it can go from 40 arc minutes to 6 arc minutes. And the idea is that for the particular molecule that we're interested in, CH, it's at the frequency of 3.3 gigahertz. And the idea is that then that causes that our beamwidth is of 30 arc minutes, okay? Which is equivalent to 0.5 degrees. Okay, so later I will show you an image of the galactic plane and some circles. And we should now go to see. Let's I'm so sorry. I think that is that my computer would like to go to sleep, so I will just y nos fuimos. Let's see, I'm trying to fix this here. Qué raro. Ah, eso fue. Regresamos. Vamos a ver si... Y regresamos. ¿Sí? Okay. So sorry for that interruption. So let's continue. Pardon me? Yeah, thank you very much. So the idea is that the second piece of a huge piece of instrumentation for this research is called the MOC. This is an spectrometer, and this is the type of spectrometer. This is a Fourier transform spectrometer, and the idea is that what this huge device, and very impressive device does, is just that the full bandwidth is then divided into some beams, and those beams we call it channels. Okay, so that's typically what we have, and in that way we can have the power at each of the channels. Okay, so we have, for example, this MOC can be subdivided into 6 compartments or partitions, and each of the partitions are used for each of the transition emission transition of the molecules that we are interested. Okay, so the first 3 MOCs were used for the molecule of interest, CH. These are, for example, the rest frequency. In the second MOCs is that we have the principal transition, the most important, we'll say. And then, since we have like other MOCs also that we can use, so what we decide is just to incorporate H2CO, which is a prebiotic molecule, just to see if we are able to have a chance to detect also that molecule. And then the other 2 MOCs, 5 and 6, we use it for hydrogen recombination lines. Okay, so that's the idea. So let's talk about the observation setup. And the observation setup is also very important. One has to be careful when designing it, because we can, for example, from the design of the setup of the observation, we can start doing some, let's say, RFI mitigation. Okay, that's the idea.
Emmanuel,
So, pardon me?
Emmanuel, this is Chris. The slides are not seeming to advance on Zoom.
Okay. Let's see if we can share again. ¿Se ve? Chris, can you check, because I know that some students can see it well. You see the 12 meter? Okay, so let's do something. Let's just unshare and share again, okay? Let's see if this is the case.
Yeah.
Yes, we're now getting your most recent slide, I think.
Yeah.
Okay. let's see if we can. Okay, so now you can see the transition.
Yes.
Perfect. Thank you very much. So the idea is that we have this observation setup. Details about the observation setup is that we have a bandwidth per MOC is of 25 megahertz, and this is divided into all the channels possible that we have for the MOC. In this case, we went for the maximum number of channels, which is like 8,192 channels. And this gave us a frequency resolution of 3 kilohertz, which is equivalent to have a velocity of 0.3 kilometers per second. Okay? So those are the basic numbers that we would like to know. And the idea is that the idea is the following: that, for example, then we use the radiometer equation, and with this radiometer equation, you can obtain what is called the integration time. So the integration time is very important because it's the time that we're supposed to observe on the source, which the hypothesis is that we're gonna find the molecule there. The times required for us to get a detection, okay, a reasonable detection at the level that we would like to have it, okay. Typically, what we say is that detection has to be at the pi sigma level. Okay, that's the idea. And sigma is just the variance of the noise. Okay, the noise of your spectrum. Okay, so that's the main idea. And the observation setup that we have is the following. For example, let's suppose that this is the telescope, and we have this position in the sky. Let's suppose that this is the position where we would like to know if the molecule is there. So, so what we are doing is just a single point position, right? Observation, in the sense that, for example, we're gonna point with the telescope at the position where we are trying to detect the molecule, that we suspect that the molecule is there, and then we're gonna do that for 5 minutes. Okay, so then we move the telescope not too far, and the idea is to another position where we highly suspect that the molecule should not be there. Okay, and the idea is that information, then we receive it and we subtract the information. Okay, and in that way we can get what we can get. We can isolate the signal of the detection of this molecule. Okay, why 5 minutes? Well, what we do is that we perform loops with this setup that is called pseudo on-off. And we have like 12 loops. So 12 times 5 is equal to 60, and that's our total integration time. So that's the idea. Okay. So here what we have is just a figure that illustrates the power spectrum. I call it power spectral density. And this is just an example of one integration time. Okay. Why do we have like two curves? So the idea is that at the receiver, we have two dipoles. These dipoles are rearranged in an orthogonal manner. All the instrumentation then receive the data, process the data, and what we have is just what we call two polarization. Polarization 1, polarization 2. Okay? So let's see. So yes.
Subtract the information. What did you?
So yeah, that's a very important thing. So we don't have a marker, but it is okay. So what we have is that when you're with the telescope pointing on the off source, right? So you're not supposed to get like any detection of the molecule, right? Because the hypothesis is that you highly suspect that the molecule is not there, right? So that will be, in a way, your baseline, okay? Then we compare that with the spectra that we obtain from what? From the position where we highly suspect that the molecule is there. Okay, we want to detect it. So the idea is that that spectra, what is going to have is what? Yeah, some baseline, but at some point at the frequency, at the particular frequency, you're supposed to have like what? Like a peak. So when you subtract the two, what do you have? What you have is just only the peak. Okay, that's the idea. Did I answer your question?
Yes.
Okay. So that's the idea. For example, this will be polarization A and B, the spectra of one Mach. Okay, and what I need to explain so that you can understand later the other graph that I have is that this peak here, we should not confuse it with the detection. This is just an artifact of how the Mach store the data. Okay, the Mach spectrometer. So this one we are not interested. The frequency line is the rest frequency line is around either of the sides of the Mach. Okay, so at these flat parts of the spectra. These tails also we typically don't use. Okay, that's the idea. So we're interested on this part and this part for each of the Mach. And each Mach we dedicated to one of the emission transmission. Okay, transition. Sorry. So as I was saying, this is a pilot study, and for example, this is the galactic center, and each of the circles represent the beam width of the beam of the telescope, and we have what 0.5 degrees. Okay, this is a spectra, and this spectra is one of our preliminary results of the detection of CH, and it's just we use as a proof of concept that the whole device and the instrumentation works well. This upgrade works truly fine, and that's the idea of what I wanted to show with this slide. Next semester, hopefully Dr. Alison Smith will join us in this forum so that she can then provide all the final spectra. Hopefully, let's see if we can get to that by next semester, our final spectra of the detection in each of these positions. Okay, so it's just an introduction. Later on, you will see those final spectra. It's going to be super exciting. Right now, we have, for example, recently, as recent as June, was published the Observatory Meerkat. They have like some studies on CH on the galactic center, but right now, for example, the pilot study that we did, 3 by 1 degrees map is considered the largest map on CH. Okay, so only on one summer. So you can imagine what we can accomplish if we are able to, again, to use the telescope, right? So that's great. So for example, something that I wanted to point out is that in each of the positions, we found out a lot of RFI. That's a typical thing of our band, which is S-band. And because of that, I told you that, for example, we used to use like 12 loops for each observation to get an hour of integration time. But sometimes to produce a spectra, we were able to use only 2 loops of what? Of 12. So you can imagine our frustration, right? Because we barely can use our data because it's so RFI affected, right? So some of the observations were okay, perhaps we dropped just 2 5-minute scans. Others, we dropped 10 out of 12. Okay, so on those ones, what we did was to re-observe to then finally get the whole intervention time that required.
What does RFI stand for?
Yeah, absolutely. It's a radio frequency interference. Okay? We can call it just interference. So yeah, thank you. So RFI has a couple of characteristics. For example, we can have a narrow RFI that affect only a couple of channels, 1 or 2. We can have also a wide RFI. These are really the problematic ones because these ones are kind of dynamic because they span across many channels. So if we put it in another unit, right, we can span from 10 to 100 kilohertz. Okay, so So that's the idea. The most problematic RFI are the ones that are close to our frequency line. So those are the ones that we cannot do much. We just have to drop the, right? Not consider those kinds of data. But if it's not in our near to our frequency line, so then we can detect it, we can clean it, and we can perform the analysis and save some data and increase our noise to noise ratio. Okay, so that's the main idea. So that's reiterating on our main goal for this particular project. This is an example of an average. We start doing the average, and the main line is supposed to be at 0 LSR velocity, and observe that in here we have like these huge peaks where, for example, this is not a detection, but this is an artifact of the data that is contaminated. Very good. So then, because of that, we would like to perform a statistical method. One way of detecting and managing RFI could be by hand. Or can you imagine you have like tons of data, terabytes of data. So can you imagine going one by one in all the different mocks, etc. So I'm doing by hand. So that's not feasible. So that's why we have to recur to statistical method. Okay. So the idea is that we have this scientist called Nira. Nira proposed this method that is called spectral kurtosis method. And he proposed it back then in 2007, back then for a spectrograph or spectrometers that consider not consider the average data. So I need to clarify something, that here I just show you the power spectral of only one second integration time. Okay, 1 second integration. But the idea is that although you see that this is quite a little bit noisy, right? This, in the way that I say in the mocks, this is an average of, for example, close to 3,000 instantaneous spectral power spectra. Okay, so although you see it that it's a little bit noisy, this is already an average of 3,000. Okay, so that's the idea. So what Nira proposed was just a method to detect RFI at real time, so not average. Okay, but then he saw the need for many spectrometers that record the data with average, such as the mock. He saw the need on generalizing the theory, and then in 2010 he expanded his theory and he created this general spectral kurtosis, which works on average data, which is our case. Our raw data is each integration spectral curve is an average of about 3,000 spectra. Okay, so this is just an unbiased estimator for what is called the voltages squared. Okay, the power, and then the idea is that what they want to do is just normalize this expectation. That's why they multiply by this factor d. This factor d is one of the parameters of the distribution of the power located at one channel. So, for example, we have here polarization A and B, and if you, for example, take the 3 second, the 300 seconds, which are in the 5-minute scans, what you will see at one channel, you will see a distribution, right, for both polarization. But that distribution is almost symmetric, has a lot of symmetry, right? And the idea is that it's gamma distributed. That's the main assumption of the method, and that's where this D parameter comes from. Okay, so it comes from the gamma distributed power spectral density at the channel. This is just the distribution at one channel. Okay, not the whole channels. And the idea is the following: that, for example, when you have a channel that is not RFI affected, your distribution, it will look like this, okay? But when you have a channel that has a frequency channel that is RFI affected, then the distribution change from this nice distribution to, for example, to a uniform or to an irregular, let's say, distribution, okay? The shape change completely. And that's what this method does. It detects when these changes per channel on the distribution of the power spectral density change, okay? And that translates in a way to what? To outliers, okay? So what this method does is good, it's just detecting outliers. And RFI on frequency channel or on affected frequency channel is just an outlier in the data, okay? That's the whole issue. So we have the estimator. The estimator have a couple of parameters. We discussed already the D, which is the shape parameter of these gamma distributions, that we assume that it's going to have the same shape across the channels. And then M is just the amount of seconds that we are considering the 5-minute scans, in this case 5 minutes. So it's like 300 seconds. And N is the amount of instantaneous power spectral density that we are averaging to obtain 1 second power spectrum, okay? Now in this case is, for example, 2,929. So it's quite a lot. So these terms are just the sum of what? Of the power. So this, for example, is just the average of the power, the instantaneous PSD, power spectral density, okay? So, for example, this is what we have in our raw data, which is the average, okay? This is just the sum of the power at for every second from the 3 seconds, and then this is the sum of the power squared, okay? And the idea is that then for example, we're gonna compute this formula, this estimator, at each of the channels. Well, how many channels do we have? So 8,000 something, right? 8,192. So with that data, we can get what? We can get a distribution for the estimator. So the distribution of the estimator looks like this. It's also a gamma distribution. It's centered the expected value is at 1, okay? And that's one of the diagnoses that your implementation of this method is correct, okay? So here what you have is just the histogram and also the fit of this gamma distribution. I call it gamma distribution, but which is a particular case of what? Of the Pearson type 3 distribution, okay? But, and that's the idea. For example, later, what can we do? So what we can do is just have the plots, scatter plots. Horizontal axis, what we have frequency channels. And then vertical axis is just the value of the spectral kurtosis estimator. So observe that all of them, or many of them, right, are around what? Around these two levels. And these two levels, we call it thresholds. Any channel with an SK value associated that is outside these two thresholds, then we flag it, and then we perform an excision of the data, okay? All these are considered outliers in this distribution. So that's the idea. So yeah, and these channels in particular correspond to the flat part of the spectrum, of the spectrum, okay? So just to zoom in so that we can see more clearly the figures, another diagnosis of that the implementation is working well is that what you're supposed to have this data is just like you're not supposed to have like a pattern. So it is supposed to look like really like random, okay? It looks like even like synthetic data, right? So, but the idea is that whenever we have RFI, then what we have, then we have a clear pattern, okay? And all these are outliers of the SK values, okay? So then, let me explain how can we compute those thresholds. Those thresholds is not something that you assign, that's it, right? That's as you need to solve an equation. So as I was telling you, these are the distributions of the SK value for both polarization. These are the histogram, which is an approximation of the shape of the probability density function. Then you feed to that histogram the probability density function, and then you take the integral calculus operation, right? So when you take the integral, you compare you get that function, and what you can get is what? Is the community distribution function, okay? that function in particular, when you draw the curve, and then when you draw this horizontal line, which is, for example, what is called our false alarm probability, the intersection of that gave us what? Gave us the lower threshold, okay? Which is these guys here, okay? That's the idea. And then, so we did it for both polarization. Observe that in the vertical axis, we have probability. Here, we just have like SK values. And then how do we obtain the upper threshold? So it's just by using the complementary cumulative distribution function, okay? Another probability function. And then in this case, observe that the intersection of this function with this false alarm probability are what? The upper values, okay? Which is, for example, these threshold levels that we see here, okay? Which are super necessary to then identify which are the channels that have a SK value that are outside of these thresholds, okay? So that's the idea mainly. Why we choose this value for the false alarm? So in this distribution, those values of the false alarm correspond, for example, in the normal distribution setting to what? To 3 sigma, 3 sigma. So in a way, what we are doing is just in this distribution, identify outliers that falls into this 99.7 percentile of the data. Okay? Yes.
So those points can be seen in the histogram, right?
That's correct. That's correct. That's absolutely correct. Right now, I didn't plot it. Why? Because otherwise the illustration doesn't look good. But the idea is that we can check that because, for example, observe that these are SK values, and these SK values they can get up to 4. In this case, 4.5. Okay, but in this horizontal axis, which we have the SK values, where those will like observe this gets up to 2, right? So this will get up to here. So truly, these values that we have here, we can see it here, right? But that's a really good question. So all these values, and one will see what really at the far end of the distribution. So are truly outliers. Okay, that's an excellent question.
And the ones that are inside of the 2 thresholds.
So those typically we assume that are channels that are not RFI affected. The only channels that are RFI affected are channels that have a spectral kurtosis outside of these bounds. Okay? Did I answer your question?
Yes, but those points are the ones that are inside the histogram for. Oh,
exactly. Yes, all these points are the ones that are inside of the histogram. Yeah, absolutely. Yeah, very good. That's all very nice. I'm glad. Okay, so then let me just now go. Okay. So once we identify this, right? So what we do is just we go to our spectra and we observe that these are the spectra, right? I just focus on these channels, and you can see that all these are channels that are affected, right? This in particular, it comes from an RFI that it drifts across the channel, right? So we perform the method and observe that the method is able to detect the channel, and then we perform the excision so that we can erase those channels. Okay. What we hope is that these RFIs are not close to our line, so that then we can proceed with the next steps in the reduction data pipeline. Okay. So now let's just see a quick movie of some integration seconds. And so you can see what typically you see in these windows when you're observing. You see the power spectrum, and you see that, for example, the RFI movie. Okay, so I will show you right now an RFI. Let's see if we can get it. Okay. So, I might have to. Okay. So I would like now to okay. So here we will see our movie, and I need to share that screen. How can I share that screen? Right now, ¿se ve? Ah, pues excelente, no tengo que hacer.
Yeah, we're looking at it.
Perfect. So, ¿se ve bien? Muy bien. So I'm gonna press enter so that you can see the movie. So let's see if it works. So for example, this is the RFI that we were talking, right? I erase the main mock center and observe that this RFI in particular is an RFI that is in one or two channels. Okay? They change very little in the amplitude, but they don't move. So which of the man-made transmitter that we, do you think that this, okay, so what do you think that is the source of the RFI in this case? What do you think? We have a narrow RFI that do not read. Which do you think that electronic device is producing this? Okay, so for us was a surprise, but the thing is, Stefano, and this has a story. The 12 meter was recently upgraded. Before the receiver was a room terminal, right? So the idea is that there are security cameras, okay, very close to the telescope. So okay, so of course, like the staff members of the at that time at the AO, right, are like super knowledgeable person with 40 or 37 years of experience. They are the RFI expert, and what happened is that when you install cameras next to the telescope, so of course you go with some devices, measure all these RFI possibilities, etc. So they were fine. We were not seeing an spectrum with RFI and this and that when we used to have a one receiver. Okay, so well, what happened? What that means that this RFI was hidden into the noise. Okay, so that's the idea. But then we operated the telescope to a cold receiver, and now the sensitivity increases in such a way that it was even able to capture the RFI produced by the security cameras. So in this case, what you need to do? So you need to go to every switch and turn it off, and do right a lot of experimentation to see which is the device that caused that. So that's the story about that narrow RFI. Okay, so that's the idea. Let me see how can I with this. Perfect. So now we're supposed to go into our presentation again. So let's see if we are able to detect and perform the excision of the RFI on those narrow ones. Okay. So what I did is just I focus only on those channels, and what we can see is that in both polarization is even what is even in the same channel, right? Channel this channel and this channel. Okay. These are the spectral with RFI affected channel, the one that I just showed you from the camera, and what these are already clear RFI affected. Okay, so here, for example, we have even, I believe that two channels. Okay, so that's the idea. Another thing is that, for example, in one polarization, the RFI looks more prominent than the other one, is because RFI and the characteristic is that it is highly polarized. Okay, so let's show you another one that is also very problematic, and and we resume our talk. Let's see if I can go to the other one. Let me modify the code quickly. Perfect. Let's save it. Let's run it, and we are ready to see the movie. Let's just put it here. Okay, so let's watch another movie and look at what happened with this particular RFI. So let's go 1 to 1. Let's do it. Okay, there you go. So what we can see here, observe that we have like one here and then this one here. This one in particular, as we move in time, what happened is not static, it's not steady. So move across channels, okay? And that's a very problematic one. So that's the idea. So then let me show you the spectrum of that. Let's see how that looks like. Let's just move to here. And then, for example, I did the zoom on the spectrum on these channels that are clearly affected. And what we can see is that we were able to detect many of those channels that are affected. And this is a scan that observed that has like what? Almost like 500 or almost 400 something, right? Channels that were affected. That's quite a lot. Okay? So further considerations, there are other type of statistical methods that I would like to jump on it and to try. The idea is that with students now we have possibly David getting to our research group, and I have also another student in UCF that we would like to perform. There is another SK method that is called multi-scale spectral kurtosis that consider information about, for example, adjacent channels. So that is great. And there is another ones that are also like based on median, on the statistic, right? The median. So that's pretty much what I have for today. Thank you very much. These are the main resources. I think that, for example, this paper has the implementation of the code. I can share that with you. I truly need to thank all the staff members of the AO at that time, at that past summer, because truly my experience was truly enriched by Phil Perilal, Arun, and all the cafeteria people, all of them, really spectacular people. So thank you very much. This is a picture where Dr. Anish Roshi is with a device that can detect, for example, where the RFI is coming, like the direction, right? And this is me holding the antenna while he works with this device, right? And of course, this is already when we were doing the observation, okay? So that's it. I will let them with this quote from my former advisor. And that's it. Thank you very much for inviting me and giving me the opportunity to share. Thank you very much.